Well, thank you, Richard, and thank everybody who's been involved with putting this together. It's a really nice event, and I'm happy to be here. Some of the issues that came up in the last talk are going to come up again in some ways, and maybe get some clarification or maybe some further confusion. I want to offer you a case study, but in offering you the case study, I also want to clarify sort of what some of the background issues are to the case. So the case is documented in a paper that we published 4 years ago, myself and a couple co-authors. The important person in this as a case is my co-author, Selva Demirel, who's now in Turkey, but at the time we started this work was working for the Federal Reserve in Washington. So it's actually motivated by a real problem in the Federal Reserve System about the management of the economy. And the real world problem is this. The Fed records various monetary aggregates, various definitions of what money is, and then wants to manipulate the economy partly by observing what's going on with those aggregates and manipulating those aggregates. So Selva worked for a section of the Fed that was concentrated, the whole section concentrated on M2, which is a particular definition of money. And their job was to give an analysis of what was happening with M2 and then what implications that might have for the management of the economy in various ways. And for reasons which I won't go into, they wanted to concentrate their analysis actually just on the liquid deposit component of M2, which is 65% of the total, and includes your checking accounts and your savings deposits, but excludes, for example, currency in circulation and less active parts of small interest-bearing accounts. So this is this monetary and reserve analysis section of the Fed that did this. And they really don't have a lot of theory about this. They have very minimal ideas about theory, and they have a lot of institutional knowledge suggested to them, or at least institutional acquaintance that suggested to them some informal factors that might affect M2 growth. And what theory they have is very primitive. It's based on a notion of the quantity theory of money, and basically the idea is that the growth of money should be essentially the growth of nominal income adjusting for a trend in velocity. And their real interest was in their specialized institutional knowledge about various other sorts of effects. And what we wanted to see in this project was to see how far we could give them some more systematized knowledge in the absence of having a deep theoretical account by trying to understand the causal mechanisms that might be at work. So how could we get along with a minimum of theory? Now, I want to switch gears here and forget that problem for a second. We'll come back to that problem and just look at a simpler kind of case so that you'll understand what the objects of analysis are and how the people at the Fed are likely to use them, or how macroeconomists are likely to use them. So the principal tool here is the structural vector autoregression. The vector autoregression is actually a system of 4 equations. That's why it's a vector. It's written in matrix form here. So we have, this is money, GDP, consumption, and investment. And this matrix is giving you the coefficients by which contemporaneously these things are related. On the other side of the equation, we have a matrix that is giving you how the lags are related. I've only put in 1 lag here, but it might have 12 lags. I mean, this is just indicative of how things could go. So the data are time series. They're developing and changing over time, and there's some structure on them, empirical structure and some other structure. So the contemporaneous relationships here are meant to be structural. They're meant to actually represent the way the economy is built in some ways, but typically, the way people engage with these is that the structure, the coefficients, and the lag terms are meant only to be data summaries. They're meant only to tell you about the correlations among the data, but they're autocorrelations because they're correlations potentially across time. The contemporaneous matrix, though, can be read as a directed acyclical graph, the way that I've written it. So in this case, you have money at the top of a chain, and money is not affected by anything below it. but money affects GDP. That's what that coefficient is telling you. Money and GDP affect consumption, those two coefficients, and all three of them affect investment. Okay, so one question is, why did I put them in that order? Okay, so the fact that it's a directed acyclical graph is reflected by the fact that there's this triangle up here of zeros, and any directed acyclical graph that you can think of with those four variables could, by rearranging the order here, be put into a form where there was an upper triangle of zeros there, although there may be some zeros down here as well. But you could certainly get all the zeros up there as long as there's no simultaneity. That would be the standard. Now, the other thing that's being assumed is that the error terms here are mutually independent. They're not correlated with each other. And one reason why you want that to be the case, and one reason why we're calling this structural, is that this is a case where all these variables, this is the entire universe of variables. The assumption is that everything that's left out of here doesn't matter. And that the only thing that drives this system are the shocks to the system. And so if you want to ask a question, what happens if there's a change in money, the only way to get it is to think of what happens to a shock there. But if you could only look at a shock with money as it was correlated with a shock with consumption, then you wouldn't be able to deliver an independent shock. Okay? And so, I mean, that's a property you want to have. It's not a property you can ask the world to give you. You have to find out whether it's really there, although you can estimate this by forcing that to be a constraint on the estimation that you're making. And that's actually what happens. By setting this order and saying that this is going to be lower triangular, then you can estimate it in such a way that you force your estimates of these things, not the real things in the world, but your estimates of them, to have that property of not being correlated with each other. And so the question is going to be that you want to get the right thing there. Now, to get the mutually independence, one thing to note is, suppose I made all these things zero and just had an identity matrix here so that there was no relationship contemporaneously among the current dated variables. Well, just as a matter of practice, with some rare exceptions, what you would find is the estimates you would naturally get from that process will all be intercorrelated. It is only in practice, by accounting for contemporaneous correlation, that you can get these things to be independent. And that's why there's a focus on the contemporaneous correlation. And for these purposes, what happens over here just doesn't matter. And so we can afford to leave it unstructured and leave it as just data summary is the idea that's going on. Now, what's implicit in this is the assumption of causal sufficiency. I've already hinted at that, which is basically that there are no omitted common causes. There may be lots of omitted causes, but for relevant purposes, no omitted common causes. This was actually something that was not talked about in this language, but was pretty well understood in the 1940s and 50s by the Coles Commission and other econometricians, but is part of the kind of forgotten knowledge in econometrics, and it needs to be reminded and brought back into attention about how strong that assumption is. Now, given our object is to estimate something like this, what are we going to do with it? Well, what we're going to do with it are two possible things. One is to calculate what happens when we get small changes to one of these variables and what their time series implications are. So these are what are known as impulse response functions. So suppose I get a shock to consumption. Well, the shock to consumption will immediately hit consumption this period, and because consumption is related to things above it with the causal arrow going down, it's not going to affect either M or Y, but it will affect I. And then I today becomes I tomorrow, and then working through this matrix affects all the other things. And so we're going to want to look at the path of how that goes through time. Now, the other thing that we can do are various sorts of counterfactual experiments. And I'll come back to the counterfactual experiments right at the end. But right now, let me just show you what an impulse response function looks like. Just look at the top one. This is the system that I wrote up there, ordered. And if you actually take data, estimate that system with a certain set of data, hold on just one second, and look at a shock to consumption, then you can trace out what happens in this case. This is a shock for, which is it? consumption.
On the bottom, it's C.
Forget the bottom. Oh, yeah, it's a response of GDP. That's it. So it's a response of GDP to a shock to consumption, yeah.
The order of these four variables, why you choose in this order, or the other order of matters?
Well, that's exactly where I'm coming to. So just hold on just a second. I mean, you're asking exactly the right question. Okay, so what are the problems here? For applying causal analysis to this? Well, there are causal algorithms that people have worked out for time series data. But many of the algorithms, certainly ones that we've been talking about this morning, are not really super specialized for time series data. They work better if you or at least are conceptualized as if you had all your data there right in front of you at a time and weren't concerned about their development. But when the data actually are time series data, one way or another you have to account for the fact that they're time series data. And it's actually particularly difficult with data which are typical in macroeconomics, data which are non-stationary. Okay? Because most of these algorithms are assuming that there are probability distributions over the data that have fairly nice properties that let you apply tests of correlation to be tests of independence. And those things typically are more difficult and sometimes perhaps impossible in other cases. A lot of economic data have probability distributions that are more appropriate to Brownian notion. And there's statistics for this. I'm not saying there's no statistics for it. I'm just saying that we haven't developed it with this in mind, and that's where we're going. Just to give you an idea of the difference, this blue line is just an independent random series. The red line is one with stationary autocorrelation. So there's time structure in there, and you have to account for it to get the right correlation statistics out of it. The greenish line here is a random walk series, and the random walk series does not have a stationary, that is stable over time, set of moments, means, or covariances. They're all time dependent. In this path, this system could go anywhere. It jumped up here, next time it could go up there, it could go down there, it could go all over the place. And so in one way or another, this is going to be a problem for us, and it's a problem for that this is the most common kind of economic data. So a solution to this problem is to get rid of the stuff that we don't want. Get rid of, since we're only mainly interested in what's happening to the contemporaneous structure, and we have all this lag time structure, we can get rid of it. Now, the Granger of Granger causality test is the first person to actually, with Norman Swanson as co-author, to apply this idea to vector autoregressions. So he kept thinking about causal things from various angles. So what we've done here is this is just a set of regression equations where we're regressing the current values on the past values, okay? And that's absorbing the past dynamics, including the non-stationary dynamics. And these estimated error terms, what's left over, will in general be highly intercorrelated, but they're going to preserve the same intercorrelation that's in the contemporaneous relationship among the left-hand variables. So in a sense, we can treat these as versions of those that have had their time series component filtered out of them. And that's the essential trick that we're going to use here. So this gives us a new object of analysis, which is these filtered variables with no time series component and just the contemporaneous relationship there. And if this is correctly specified, then these are going to all be mutually independent. So now we come to your question. And how do we specify the order here is one question. And somebody mentioned identification in the last session. So the fact is that we have to have this many restrictions. So there's 6 restrictions. In this case, if we don't have those 6 restrictions, we can't even estimate this system. That's a minimum condition for any system which is going to be estimable. And that's well known to econometrics. I'm not going to talk about that. But the condition is we have to have at least that many restrictions. We can have more. Now, typically in this literature, what most economists have done is say, well, we'll just get by with the minimum. We'll use the just identified case where we have exactly enough restrictions, so all these things are thought to be non-zero. And then you have this question, well, how do you put those things in the right order? Because I just put them in an arbitrary order, and I could have put them in a different order. And what typically happens is people say, well, we have to go to economic theory. But economic theory doesn't answer questions like that. I don't know any economic theory that actually answers questions like that. So what they really do is they tell you just so stories about why one thing ought to be ordered ahead of another. But for every just so story you can tell me, I can think of another one, maybe a little bit more difficult to believe, but maybe not, that would give you a different order. So, one would like something better, and that's the point at which we want to apply some kind of causal search methodology. Now, there's a further problem here with this typical way that economists do this, and that problem is, think about all the different orders you can put here. How could you distinguish one order from another? And the problem is that they're all observationally equivalent. And to an econometrician, what that means is every model, no matter how I put the order in there, as long as those things, if there's no just enough restrictions to identify it, they all have the same likelihood. Now we can put this into graph-theoretic terms, into this kind of causal search terms, by thinking, well, what's the graph of that VAR that I had? Well, the graph is this. M causes Y, it causes I, it causes C. Y causes C and I, C causes I, okay? And you notice it's a densely connected graph. And we put particular arrows on them because that's reflecting the order that I put those variables in. But the point here is that this graph is densely connected, and although we have arrows on it, there are no unshielded colliders in this graph, which is exactly the case which this literature tells you is observationally equivalent. So observational equivalence can show up as the identity of the likelihood function, and it shows up graphically as this densely connected graph without unshielded colliders. Now, it makes a difference, though. Despite the fact that they're observationally equivalent in a set of data, it's going to make a difference to the Federal Reserve which way these things are. And you can see that by looking at these graphs again. This is the one I showed you before, and this was with the order I showed you before. But this is the same set of data with a different order. This is money to consumption to investment to GDP. And when you have this order and take exactly the same shock, instead of having everything trending up, you have everything trending down. So it really makes some difference which way you get this right if you want to do the thought experiments. Well, no, it shouldn't be too scary because we're offering you a solution.
Just use the top order.
Yeah. That's what that's how it is normally proceeded. So here's the idea. And what we're going to do is we're going to run the search algorithm on this system. And now you'll notice here I filled in all of the coefficients. So all the links are potentially there. But what the algorithm is going to tell us, if it tells us anything, is that we can put zeros in a lot of these places. And what we really want to know is where the zeros go. And then having established the contemporaneous order there, we're going to move that contemporaneous order back into our original target, this SVAR, and then we'll estimate this by ordinary econometric means to get the coefficient estimates, and then we can perform our impulse response functions and counterfactual experiments on that object. Now I'm going to raise some other problems, I'm going to do some other things with this, but I want to go back now and just show you the actual case and what we've done and the issues that arise in that. So in the actual case, these are a set of variables that are actually suggested by the practices of that section of the Federal Reserve. These are the kind of things that they were monitoring and looking at. There are 11 of them. We got them running over a period of about 15 years. This date stopping there is because there's an institutional reform, and the institutional reform is a harbinger to the 2007 crash, which has completely changed how monetary policy is conducted. And we don't know. It's a big institutional change, and we don't know whether they'll revert back to where this is relevant or not. It's hard to know. So I'm a primitive here. I don't use any of the sophisticated algorithms. I'm just using the PC algorithm, which is assuming no latent variables. And this is our initial our initial graph. And I think there's some things to be said about this graph. The first thing to notice is that there's one edge which is undirected. And what that's going to mean is that we can turn the arrow either way, and we'll have graphs which are in the equivalence class. And we're going to have to make some decision about how that arrow goes. Another thing to notice is that we have these two edges which are bidirected. Now, how can that happen? Well, it could just happen from small sample problems. I mean, this could be a purely statistical artifact, or it could happen from an omitted common cause. What it could not be, let me emphasize, it cannot be simultaneity here. And the reason you know that is if it were simultaneity, then a PC algorithm, having found this link, would also find a link there, and would not give you a double-headed arrow here, but would give you a straight arrow, a straight edge there. That's a marker for how simultaneity shows up in models like this. And actually, when we wrote that paper, I did not fully understand that point. So this is a revelation to me after working a little bit further on this. So this is an interesting point, because economists start off with the presumption that everything depends on everything else. So they expect to find simultaneity everywhere. And actually, in many practical cases, you just don't find it. You just find much more structure as you do here. Other thing to notice is this is the core inflation rate. And it really is contemporaneously unconnected to anything. It's not unconnected to everything in the time series, but it's unconnected contemporaneously. So there's nothing in here that jumps off at us as being impossible to accept. Now, one question we have, and this comes back to somebody's question about bootstrapping, is how reliable is that graph? Should we trust that graph? And we thought about various ways to do that. I'm not going to go into this in detail. I'll show you very briefly, because I don't have time, what we did. I'm not sure it's even the best thing to do, but it's what we did. Basically, we said, look, this object is not the structural VAR, it's the VAR. It's the current things depending only on their lags. And the idea of not structuring them means that these error terms, which we're going to estimate, are all going to be intercorrelated. They're very similar to the thing I showed you before about how we filtered the data. Okay? But this is a fact about the world. I mean, a fact about the data that we can just estimate, and we know what it is. And what we do is then generate new data sets from this in a kind of bootstrap procedure where we take the parameters that we estimate, hold them fixed, and then we take the error terms that we estimate and we draw out of those error terms by column. So we draw all the ones from one period and then throw it back and then draw again. And drawing them by column is to preserve the intercorrelation that they have, which is the important feature of the data here for us. And we do that 10,000 times, and we apply the PC algorithm each time, and we get a new graph every time. And this table summarizes, there's actually 55 edges here, and we don't have them all summarized. The ones we're not summarizing are the ones that actually are just not picked. They have to be picked more than 10% of the time before they show up in our graph. And so we actually give you the complete edge distribution of which way between any pair of variables the edges are directed. And then we give some summary statistics for that, and this is just a subpart of that table showing you the summary statistics. So this tells you, in this case, this edge was found in 100% of replications. It had a definite direction in 35%, and it had an 11-point preference for the arrow running from the 30-year mortgage rate to the refi index in that direction. Okay, this is what the original application to the data actually found. So a lot of these had no edges. Okay, so what are we going to do with that? Well, I'll show you. First, what we're going to do is we have to orient the unoriented edge. And so we're going to look at it under, there's just one edge like that, and we're going to look at it under both cases, oriented one way, oriented the other way. We also have the bidirectional edge. And with the bidirectional edge, because we are not going to suffer from an identification problem, we're just going to put that edge in as a bidirectional edge, even though I know it's not simultaneous. But we're going to initially estimate it as a bidirectional edge. We're going to, if you then estimate the the system there, you're going to get a very low p-value, which basically says you can reject this model. The model, that the graph that we have tried to estimate based on what we found is rejectable. So the way we deal with that is we're actually more afraid that we're leaving stuff out than we're putting stuff in. And so what we do is we go down our list from our bootstrap and we take the edges that were not found in the initial search, but have the highest rate of showing up in the bootstrap, and we add them to the system. All the borderline edges that come in at above 10%, and in fact, we still get rejection at 10% when the arrow goes from the mortgage rate to the refi rate in that direction. In that case, we actually go down to 2.5%. So we really become very promiscuous in putting edges into the system. And then we conduct a general to specific search of a sort very similar to the kind of searches that are done in kind of David Henry LSE type methodologies. It's not a proper LSE search, but generally what we're doing is we're looking at each edge and we're saying, what's the t-statistic on that edge? And if we take the one with the lowest t-statistic and we drop it, and we see whether we can pass a test then of that restricted model against the most unrestricted model, against a just identified model, which is the most unrestricted model. And with the initial search, we fail the test miserably. When we've supplemented it with these extra edges, we pass it. Okay? And then we do various simplifications. So we take out this edge and then the thing won't converge, so we have to put it back. And then we take out the next edge and we actually get the p-value moving in a good direction. And we keep doing this, omitting low t-statistics until either they're all statistically significant or we violate the test again. And this is where we stop. This one, because we're using a 10% significance level here, we've gotten below the significance level. This is the critical point of the last omission we can do. Now we did this one for the refi running to the mortgage rate. If we run that undirected edge the other way, of course we get the same rejection in each case because that's the observational equivalence. If we supplement it with all those extra edges, we still get rejection. We just can't make it. No matter what we throw into it, we can't make that an acceptable direction. So we end up with just the outcome of this search as our model, and that's it. It looks an awful lot like what you saw before, except now this is directed, and these bidirectional edges are now unidirectional edges, and we've added one more edge, that's all, from M2, own rate of interest on M2, to the S&P 500 index. And that is our structure that we then use. So to give you an idea of what we've thrown away, I've ordered these so they have a lower triangular form. And you can see that all these zeros are showing all the restrictions that putting causal structure has allowed us to get onto it. Well, the next thing we do is say, well, look, there are other search technologies that are not of this causal structure that will help us with the dynamics. Once we've gotten the contemporaneous order, we can apply some of the traditional regression-oriented, statistically but not causally based search technologies without much worry. And the ones we're applying are basically in the family of the LSE approach of David Henry, and I'd done some of my early work on making machine versions of those that then Henry ran with. It's actually Henry's program. It's the Autometrics program that we're actually using to implement this. So we do what the people in the structural vector autoregression literature typically don't do, which is to add a lot of structure to the lag parts of it in this particular instance. So we're trying to get as fully structured a structural autoregression as we can. And this summarizes our results. The really dark ones say that there are contemporaneous relationships between these causes and those effects only. The intermediate, contemporaneous and lagged relationships. The medium one says contemporaneous only, and these pale ones are saying they're only lagged causes. So the fact that that is a very pale looking diagram is telling you how much structure we've put on it, especially the white bits are saying we've really put structure on them. But even the paler bits are telling you that we've created quite a bit of structure on them. And just to give you a contrast, look at what this picture would look like for the typical macroeconomist structural VAR, where they just put an arbitrary order in. Okay, that's the picture that we're contrasting it with. So this is telling us how much information that they've left on the table that we're taking off the table. So now what do we do with it? Well, I showed you impulse response functions before, and these are actually the typical things that the Federal Reserve is worried about. What they're worried about is that they have some handle on which they can control things that we care about in the economy. And the major tool that they had for controlling that was, up until the financial crisis, was the federal funds rate. So whenever they had a policy meeting, what they were going to say is, we're going to raise or lower the federal funds rate by a quarter point, or sometimes by a half point. Okay, if they were feeling really aggressive, that's how they operated. What happened with the financial crisis was that they lowered the federal funds rate till they essentially hit a lower zero bound. You can't make a nominal interest rate go below zero except in some weird ways that don't bear on monetary policy especially. And now when you hear them talking about quantitative easing as a monetary policy, that is just a way of saying that we're going to move our attention from our typical short-run policy rate to long-run policy rates, and we're going to do as many asset purchases as are necessary to get that long-run policy rate where we want it to be. Now, whether that works or not is another story. I have a view about that, but we don't need to go into it. But this is the pre-crisis thing where the policy tool is the federal funds rate. So one thing you might want to know about the properties of the system is, well, what happens when we give a shock to that tool? Because tracing through that shock is going to tell you something about the mechanics of the system. I'm not saying that policy should be implemented by shocks. There's a contradiction there because you can't implement a systematic policy by random shocks. But it's kind of a test to show you how the things are connected and going through the system. So the things that they're interested in principally are inflation and real outcomes. So GDP, in this case, in our system, we don't have GDP, we have industrial production, which is a very good marker for GDP. So these are the impulse response functions, the heavy black lines in each of these cases, are the impulse response functions to a 25 basis point, that is a quarter point, it's pretty much standard federal funds rate shock. And the dotted lines on the outside are the standard error bands for that. So one thing that's interesting about this is if you, in our system, if you give it a federal funds rate shock, and this is the inflation rate here, the standard error bands of that process, which looks very dynamically interesting, straddle zero everywhere, which is suggestive of the fact that there's not information here that they can distinguish the effect of that policy shock from nothing at all happening. Now, the bottom one here is the impulse response function of industrial production to a shock. That's again the dark line, and the dotted lines are the standard error bands. And actually this is 1 quarter, I think these are quarters, maybe they're months. No, they're months. So this is just 2 months after the shock. The standard error bands are now bounded away from zero. So we're actually getting a measurable but quite uncertain positive effect from a federal funds shock at a short horizon. But not only does it return very quickly, which is actually what you're supposed to expect. I mean, economic theory suggests that, but it also is rapidly surrounding on to zero. So there's nothing inconsistent here with what, as economists, we think of a priori, but what it does tell you is that the effects that they're after are inflation, we don't seem to see much evidence of, and that the industrial production or real effects are short-lived. Now, the other thing you can do is ask various counterfactual experiments, and there's different ways you could do that. If you have a fully structured model, anything you can change in the structure could be a legitimate counterfactual. Well, one way we wanted to think about this was this whole section exists to talk about M2, to talk about the effects of a particular set of assets on the economy. So what we did to get at that was basically to shut them down. We were interested in the liquid deposits part of M2, and lots of things were flowing into liquid deposits in our structure, and I didn't point that out to you, but none of the things that they thought were important was quite interesting. But lots of things were flowing out of it too. It looks like potentially there were lots of causal influences. So one question is, how big are those causal influences? And one way of quantifying that is, we're almost done. One way of quantifying that is to shut it down and say, okay, let's cut out all the out arrows from liquid deposits and then see what happens to the impulse response function. Do the same experiment with and without liquid deposits being allowed to affect anything. And what happens is this is this other lighter line. And the point is, yes, they're different, but they're different well within the standard error bands, which means that, statistically they're virtually indistinguishable, and absolutely the differences are extremely small, which is highly suggestive of the fact that a lot of intellectual resources in the Federal Reserve were put into monitoring something that seems, in any practical sense, to be disconnected from anything that they think that they should be able to control, and they might want to think about reallocating the resources. That may be why Selva decided to go back into academia. So, just very quickly, there are some open issues here about these kind of things in general, not particularly about this case study, just things I'm interested in. And one of them is all this graphical approaches have generally been about directed acyclical graphs. And there are people who've worked on cyclical graphs, but that's an open question, and it's a particularly important one for economists because we believe in simultaneity and cyclicality. So I've done some work recently on a paper that's involved with that. And the other thing that I'm getting very interested in now is the problem of these non-stationary variables, which are very much characterized macroeconomic data. And what happens with non-stationary data is that various variables can have common trends, but the common trends seem to be latent variables. They're not generally identifiable with a readily observable data, and this is something which has not been either noticed or adequately treated by econometricians. And so I am working with somebody in Copenhagen now that I hope we can make some progress on that question. So, thank you.
So, if I understand correctly, you have a two-stage process to discover causality.
Yes, and to identify the structure. Those are equivalent to me.
Yeah, so in the first stage, you remove the time course effect.
Yes.
And then you find the causal structure. But when you remove the causal effect, so you don't do it simultaneously, you don't have an algorithm. I don't think anybody has to do it simultaneously. But so the way you do it, I wonder, you're only entitled to use causality in the simultaneous, not from different time points.
That's exactly right. That's exactly right. So let me just go back and look at the picture just to clarify what's going on there.
Okay, so from time point to the next one, it could be, all the associations could be due to compounding.
Let me just be real clear about what we do.
I don't know if I explained it well.
We first set aside all the dynamic structure so that the only thing that's left in the relationship, we would basically concentrate out all the past behavior. There's a statistical theorem that explains how that's legit. And then we structure just the contemporaneous causal relationship. And that means putting a lot of zeros into this matrix. That is then fed down into the similar parallel matrix down here. But we've said nothing at that point about this structure. Okay, we left that unstructured. But then we do an additional step, holding this structure, not the parameters, but holding the causal structure fixed. We then do a search across this structure in order to put some zeros in here that adds that past structure that you're looking for. Now, there may be better ways